And actually,
You're
so Jeremy has his hand raised first. Jeremy, go for it, sir.
Please.
Hey, Ken, thanks for that presentation. I had a couple questions.
Yes, please.
That was great that you showed the standard model and, a little bit about, the particle, some more particles and what the graphs look like, then showed how to take the graphs and put them into the matrix form, and then showed kind of how you get these particle interactions that we get, we see in the typical particle accelerator experiments from these matrices that you get with this whole graph formalism. But I'm still unsure how you get things like charge, like where does particles charge come from, also mass, where does the mass factor into the picture, and like charge and mass. Why don't you start there?
Okay, great. Those are fantastic questions. So generally in Phoenix, the way that we talk about charge is using the loops and the arrows, right? So the idea is that every vertex either has, loops, arrows, or some attachment to another vertex. And so what we call the tadpoles, the loops and the arrows, how you count them, that's what constitutes charge. So now the question becomes, how is it that 3 loops somehow is magically a -1 electrical charge? Or for that matter, why 5 loops actually constitutes a +1 charge? So there's a linear relationship between the charge of a particle, how we constitute charge in regular modern physics, and the number of tadpoles that our graph has. So that, well, that's a linear relationship. So that linear relationship is how we get there. So the question is, okay, so what is this other thing where you're using tadpoles and loops? That actually is called hypercharge. So there's a construction of the weak nuclear theory that uses this idea called hypercharge and relates it to something we call charge, how we measure charge. And so what we show in Phoenix is that the hypercharge mechanism is what Phoenix is actually using as tadpoles and arrows, but there's a direct linear relationship to regular charge. So again, so if every particle or graph that has 3 loops on it always has a -1 charge. Every graph that has 5 loops on it, so no matter what it is, if it has 5 loops on it, it is always a +1 charge, right? Same thing with the antiparticle. So if it had 3 arrows on it, that would be a +1 charge. If it had 3 or 5 arrows on it, it would be a -1 charge, etc. So we're showing that there's a linear relationship between something we call, well, physics calls hypercharge, and the charge that you expect these particles to have. So that's the relationship between charge. Now, when it comes to the mass, the way Phoenix talks about mass is that we talk, and something we talked about actually in the prior presentation. In that prior presentation, we talk about cyclic charges. And what that is if you take the matrix, right, the matrix construction, and you take its trace, which is you just add up the diagonal of that matrix, then that thing that you just calculated is what we call a charge. That's the number of tadpoles and arrows that are associated with that graph, right? So if I take the matrix and I just add up its diagonal, the diagonal itself of that matrix is telling you all about the number of loops and the number of arrows. And so adding all of those together gives you the total number of loops and arrows sitting on a graph. And that's what we call the charge, right? The electric charge or the hypercharge. If I take that same matrix and I square it, and then I take its trace, I get another conserved quantity about that system. We call that the spin. If I take that same matrix and I cube it, and then I take its trace, I get another conserved property, and that's what we call the mass. So the idea of what constitutes these other conserved properties of a particle are very simply stated in Phoenix as taking the matrix of that graph and then finding these higher order powers of it, and then tracing them out.
Okay.
And yeah.
Drew here. Hey everyone. If I may, we can say these graphs we're looking at essentially contain this connectivity and information and the signs of what we saw, the loops and arrows. We know, as we saw from the presentation, we can represent that as a matrix. Essentially, a transformation on that matrix and successive transformations essentially yield these integer characteristics, which are lockstep with the characteristics of the physical particle. Is probably the way to wrap that all up, I would say.
Thank you, Drew. I appreciate that. Yeah.
Jeremy, if you want to keep going, that's good, or I can skip to a couple of questions I'm seeing in the room.
Yeah, well, and Drew, I would love to have you share. You've been relatively quiet, and that's totally fine, but yeah, I would love to have you share more.
Yeah, Ken, it looks like we've someone kind of made a reference to, oh, look, this is the hieroglyphics, which we can presume that this is, people can look at this and say, oh, interesting, it seems like this is, we're just naming particles, and that kind of makes sense, but we can also share and go into what's going on more deeply. And I can tell you, as a computer scientist, when you can represent a framework with a fewer lexicons, smaller pieces, and have it cover more and say more, that's not a rewriting of it. That's a profound re-expression of it in a fundamental way that informs on new things. Sure enough, this same, we went through kind of fast in the beginning, but the implications of being able to enumerate and express different kinds of particles other than the natural ones that we see certainly has profound implications. And Ken can go into that more on specifics.
Well, no, if I could interject, and so Avatar Ang just pasted this into chat, and this is what folks had asked. A few folks had asked this the last time. He was wondering about predictions, and I think predicting new phenomena would be the best, or leverage would be amazing.
Yeah, Ken, would you mind if I went into? I could go into the muon electron. We would go into that on the surface level.
Sure.
And then there's the dark matter part, which we were sort of been teasing around here in this, which is appropriate for subsequent ones. But I'll do both of those briefly. So the first one is, as some may or may not know, in the LHCb, right, there's an open discrepancy right now. There's the ratio of electrons produced versus the ones of muon produce. The standard model predicts a 1-to-1 ratio. Yet what's coming out is around 0.75, 0.8 kind of ballpark, and there's been increasingly convergence in that kind of neighborhood of that ratio. Well, Phoenix can actually explain that precisely in that exact neighborhood, and that's basically a product. If you look at the muon particle and the electron, and you saw some of those reaction diagrams, if you look at the particle, what's going in the experiment, and you perform the sort of numerical permutation of all the possible constituents of this thing that they put in, and you come out with all the possible products, and then in two of those bands of products happen to be where you're creating an electron positron, and then muon anti-muon. And so the ones in the experiment, they're measuring the outcomes of those two particular reactions. However, in Phoenix, the ratio of those two products are lockstep with the combinatorial probabilities or the numerics of what is producible. So the ratio of those turns out to be around 0.8 in Phoenix. And the software utilities that we're building around this demonstrates that, and that's sort of in a forthcoming presentation, a lab presentation where we can do this stuff. So that's really quick. That's the lepton universality one. And then briefly, we'll cover in more in the subsequent ones. The dark matter issue is, dark matter does not interact. Well, what's really happening, if you really think of these particles as numbers, and that prime numbers correspond to particles that can't be decomposed into other other numbers, like by definition of prime, you can start to imagine that the set of numbers or particles that are larger that do not interact with the smaller ones, you can start to see how some of that makes sense, and that the statistics of that, we're working on this model, but the statistics of that reflect the ratio of dark matter to visible matter that we see.
That was well said. So with respect to the dark matter stuff, with how we like to represent it, as Drew was saying, is that there are particles that can decompose. There are graphs or particles that can decompose in Phoenix, and then there are graphs that don't decompose at all. And those graphs that don't decompose, we call them primes. And those prime graphs actually represent fundamental particles. So for example, in Phoenix, a proton is a not decomposable graph, which means that it represents a particle that itself cannot fall apart once it's been created. And what that means is that the proton doesn't decay. And then what that means is that we treat the proton as a prime.
Yeah, and really quick, combinatorically, if you look at the graph of the proton, there's no other way to construct a graph with constituent parts such that you can interchange the pieces and still have all the characteristic traces that you heard about stay the same. Mm-hmm. So this is really the exciting things that we're seeing in this is that the implications of the math and the combinatorics are this beautiful reflection and expression of what we see out there. In the chat, I'm seeing peer review things, and we're absolutely excited to move that along further, and where you're hearing it now. And what helps accelerate that progress is as people who want to deal into the project and sponsorships and so on. So if you like it and want to hear more, by all means, please reach out to us. But we're happy to take the toughest questions because it's pretty exciting stuff.
Well, yeah. Now, do you think I think Remy had a question. Can I put Remy on?
Yeah.
Hey, Remy.
Hi, Ken, and hi, Drew. That's a great presentation. What I'm seeing here, first of all, the first impression I'm getting, you've got a much better organizational system for the fundamental particle zoo. I very much like all this graph theory.
Yeah, right.
Brilliant. And what Drew said as well about conservation, what you said it too, Ken, about the conservation laws and how you're taking the trace of progressively higher matrices. I mean, that is so fundamental and that is so neat.
Thank you. Yeah? Oh, by the way, just as an aside, that technique is being used currently with string theory. So if you were to do a little research with first of all, the string theory in the 90s and the string theory today, I'm sorry to interrupt you, but that technique of taking the matrix and squaring it and cubing it and taking it to higher orders and then tracing it out is a actual technique that we're using in string theory as well.
In that case, have you spoken to people like Michio Kaku? I think that's how you pronounce it. You know, one of the founders of string theory. Have you got any sort of synergy, bounced anything off him? Is he picking this up and seeing any parallels?
Actually, no, we haven't communicated with Michio. I think that the core of the sort of the people that we've been looking at with string theory have been people like Douglas Stanford and people out at Stanford University, as well as there's a whole other group out at Harvard University, which are working with the ADS-CFT conjecture. Sorry.
It's about the only useful thing that's come out of string theory, ADS-CFT. It's not a lot there otherwise. There's bits of pure mathematics, bits of group theory, but it hasn't made any predictions. So they're tending to just protect their field. Keeping outsiders out.
Well, on some level, what they've allowed to happen is for a whole new, younger stream of researchers to have at it. So, for example, sorry.
No, sorry, I just realized I haven't got my screen on. I'm going to get nagged by Tim in a second.
Yeah, I was waiting to, yeah. Well, because if you don't have your camera on, I get nagged by Mark Sokol. He said, Tim, get that camera on. I'm like, okay.
I already did that in the chat.
See, it's, yeah.
I just wanted to ask you, what you might need is a monograph.
Okay.
Have you? I was given the example with Dirac with his principles of quantum mechanics in about 1928, and it was all very new then, and people go, "Oh, matrix mechanics, you know, I can't see how it connects with the real world," and now it's of course so standard. If you could get a monograph together, get it through a good publishing house, yeah. But obviously the peer-reviewed papers as well.
Yes.
Are important. But I'm seeing this is like a Solvay moment. This is something really important. What you're doing, what you and Drew are doing, is really important.
Thank you.
It's just so damn neat. It's really, really neat.
You know, if I could jump in really quickly, and I hope I don't sound, I feel ignorant saying this, but
no.
I know you guys both are from the information technology. When you present this, you were way above my head, but it almost reminds me of it seems like you're applying a form of algorithmic compression to physics. Would that be? And so, but that in some ways, I think that might tend to confuse traditional physicists, because they kind of come up with a model and they're like, this is the way things are. But right, one of the ideas with algorithmic compression is that you're replacing, you know, I mean, complex instruction sets with reduced instruction sets. Right?
Yeah.
So.
Yeah. If I may, what really cool thing about this is that, you know, we talked about in the muon versus electron, when you look at these graphs, and I've been doing a lot of work lately on encoding and canonicalization. What that means is being able to name a graph as unique versus others. And so a graph that has more sort of symmetry is going to have a lot more sort of, well, group symmetry than others. And it turns out that ties in very intimately with the counting and combinatorics of how these pieces can fit together probabilistically. And the beautiful thing about this model is it turns into this game of numbers and combinatorics and statistics, all with integers. And so that the things that we measure and see are just these probabilistic outcomes out of all the possibilities. And anyone who's in, you know, physics this already rhymes with what we already know. It's just that now this is a way of shifting it into this graph domain instead of the field domain. And a lot of these, like I said, these complexities kind of drop out into a way that things can make a lot of sense. And it's almost, as an outsider coming in, you know, a year, 2 years plus ago, as a computer scientist, you know, I remember when I saw the, beta minus decay, and I'm like, well, that's just, you know, it was more than just the renaming. Like, this isn't renaming. This is a profound statement on the combinations of how things can go together, right? And it's like, oh, that's interesting, and that because, you know, there's just a really cool natural expression, as you're saying, Tim, of encoding and degrees of symmetry, things that are very sort of lockstep and fundamental to the core of discrete math.
Yeah, and the idea that a graph that, you know, when you go, okay, that's this particular particle, it's not simply a naming system, because what we can show is that within a very discrete transformation, what we call an orthogonal transformation, that particular graph becomes other graphs. And it just so happens that the other graphs that it becomes meet up with the electron or the proton or these other things. And then when you ask, well, my God, that was a neutron, we could classify that original graph as a neutron because it had two down quarks, one up quark. And then what it transformed into had two up quarks and one down quark, and that's what we call the proton. And somehow these two graphs are actually giving rise to each other. That's not a naming quality, right?
Well,
so when we
it seems in some ways too that this might almost, I mean, it seems like this is the kind of thing that might scare a lot of traditional physicists, and I think they're used to kind of being on the top of the pile in terms of complexity and stuff like that. And the impression that I get, again, as a layperson, the impression I get is, you're taking that top of the pile, right, where it's super complex, and you're saying, okay, now we're going to do meta-analysis on it, you know, and which takes it to kind of a whole nother level.
That's right. That's right.
But you know,
Sorry.
I should apologize for interrupting Remy earlier. Also, I think he had more questions. If it's okay to put him back on.
Absolutely.
Yeah, thanks a lot. Jeremy's put his hand up as well. Oh God, what was I thinking now? Yeah, the first one was the photon. You have two vertices.
Yes.
Electron has one. The electron seems to come out as very, very simple in your theory. That's with right. Just the 3 loopbacks. Photon has 2 vertices. Why is that, please?
Well, the reason why is because in this particular graph construction, the 2 vertices, and we'll learn this later on, but these 2 vertices actually, okay, so the construction element, when one says, well, how do you define the state of this particle? The way you do it is through something we call a cyclic generating function. And the elements of that generating function, it's a polynomial, right? We've got a z squared, z cubed, z to the 4th. It's a polynomial. And the coefficient in front of that polynomial is the trace of the matrix, or the trace of the matrix squared, or the trace of the matrix cubed, or the trace of the matrix to the 4th power. But that's what sits in front of the z squared, the z cubed, and the z 4th, polynomial. Okay, so what's important?
To be frank, I'm not really seeing that, but I'm sort of thinking, what does it mean? The photon is an absolutely fundamental particle, as is the electron. I would have expected it to be very simple in its description, and I would have expected, if I'm getting this all wrong, I would have expected the vertices to somehow be related to the spin. So you'd have, the spin is related to polarization.
Yes.
So you would have had, say, for 2 polarization states of a real photon, you would have had, say, 2 vertices on, say, a virtual photon. You would have had 4 vertices.
Yes.
And for a graviton and so forth. But I think I've got the wrong end of the stick on that. I don't think I understand in that.
Okay, so sorry. So the polarization of the photon, if we go to what we call the gamma vertex, it's a single vertex that has 3 connections coming off of it. And those 3 connections can, connect obviously to other vertices, but there's no loops or arrows on this thing we're calling the gamma vertex, right? And what we find is that there are 4 different polarizations of that gamma vertex. And the polarizations in this case is how are they connected to the other vertices. So so it can be connected. One might represent the connection as, maybe information coming out of a vertex or information going into a vertex. And so when you look at the 4 different ways that you can adjust for information flowing in or information flowing in, or
sorry to cut in, but are you saying that by having this connection between the vertices, these gammas between the vertices, you're deriving your spin? Because my question, Ben, is that the electron is just this point vertex with these loopbacks. How does that get its spin?
Well, the way we characterize spin is we look at the matrix squared. Okay, so how do we characterize conserved charges for a particle? That's the first kind of a question that you're really asking. That system of conserved charges lives on this thing we're calling the cyclic generating function. It's really a polynomial where the coefficients of the polynomial are simply the matrix, the trace of the matrix for the first coefficient. The second coefficient is the matrix squared and its trace. The third coefficient is the matrix cubed and its trace, etc.
And I can jump in too.
Yeah.
Yeah, and I think what Ken's going towards, as we were talking about, and to Jeremy's question, the characteristics of a given graph or a particle are really are one-to-one with this traces integer vector, right? Which is essentially this output of this series or sequence of matrix transformations. And it's that integer vector which is really associated with the physical properties of the particles. And it turns out that graphs that don't have any loops or arrows, i.e. graphs with a zero down that whole diagonal, those have properties that we recognize as conventional electromagnetic energy.
Yes.
And that the easiest formed one is a 2 vertex with 3 edges that obeys all the rules.
That's
and
right.
the fun part that we want to get to later is that, and, the dark photons and all that stuff is the ability to construct other particles which have photon-like properties because they don't have loops and arrows, but it's because they are not this 2 vertex thing, right? So hopefully that makes a little more sense. That
it's beginning to make sense. And just I want to yield for Jeremy, but just finally, just really 3 kind of related questions, if I can remember them. Like 3 related questions. Things like, someone said calculations. Can you predict things like branching ratios in decays?
Yes.
Straight from your graph?
Yes.
Okay. What about a correspondence principle? Can you make a megagraph and say that approximates a classical particle?
Oh yeah.
Could you, in principle, do something like that, and then it would then move into the classical world? You can do something like that?
So the classical particle construct is normally what we would call the field, right? So in particle physics today, we're not really talking about particles, we're talking about fields. And so the question is, how does one construct a field from these discrete things that we're calling particles? And so we demonstrate, in fact, we talked about it the last time when we were talking about integration techniques. The integration technique takes a chunky particle and turns it into a field, right? And that's really what you're talking about. So there's a technique that we would normally call integration that can take this alphabet of particles and turn them into the fields, as well as the field dynamics that we normally talk about in particle field theory. I hope that
would be, excuse the terminology, sort of paradoxical terminology, but that would be a classical quantum field.
Yeah, that would be the right. That would be the what I would understand that you're saying is the classical way of talking about particle physics, right?
Yeah.
Or are you saying something?
One step back, because it was quantum field theory with second quantization that made no distinction between particles and fields. They were one and the same.
Right.
Whereas in classical physics, you have fields and you have particles. Yes. So one step back, even to that, can you get a correspondence principle to say in the limit, this all goes over to conventional classical physics? Can you do such a thing in principle?
Yes, and by virtue, again, for what you're talking about with classical, what we're really talking about are fields. And the fields in particular are sort of our size, sort of gravitational, suns and people, etc. And so I hope I'm understanding that correctly. Versus when we're talking about quantum fields, we're talking about some other set of fields that are a lot smaller. Okay, and then when we talk about our particles, we're talking about these chunky things that don't even exist in terms of what we talk about with quantum fields. But normally the fields that you're talking about are, size us, where we're talking about temperature versus talking about, kinetic energy of a particle, right? So let me just make sure I'm understanding that by classical, you mean macroscopic.
Not necessarily. It's the
Not
idea
necessarily,
of,
okay.
So like a quantum of action. I mean, you could talk. You could talk about, say, like the Schwinger limit with paired curation.
Okay, so
that's massive. That's sort of a massive field, isn't it? It's something like 10 to the 16 volts per meter.
That's right.
So
that's right.
It's not to do with the size of the thing. It's to do with like the quantum of action, isn't it?
Yeah, it is. Or the quantum of action, which we can also talk about here, which is what we call our transformation matrix, but or the Hamiltonian. But the idea, at least, is that there are, I guess, levels or size scales. So what we're doing here when we're talking about these particular graphs is we're talking about a size scale that is not what we talk about in normal quantum field theory. And so what we're saying is that there's this substrate of pieces that can be assembled as virtual discrete chunks that give rise eventually to field theories that we talk about in quantum mechanics, which then give rise to these higher order fields that we're talking about when it comes to molecules and atoms, etc.
I'm just going to, one more thing, then I'll yield to Jeremy. But
Sure.
People are probably going with the notion, thinking that an electron is made of some loops and stuff like that. It's purely a description. It's a mathematical description.
That's right.
People also think Feynman diagrams no, it's a graph. The Feynman diagram is a graph. It's a graph. It's a summation of processes to get from one point to another. So it's not literally. It doesn't literally mean that say you had a rather complicated diagram for a neutron. Say doesn't mean that somehow in the neutron it's some stick diagram. It's not that.
Thank you for raising that. I want to make that point really quick. That, like someone had mentioned, are these Feynman diagrams? Like, yeah, Feynman diagrams are associated with a process and time and space. Remember that when we introduced it in the beginning, this is a different domain. This is essentially a conceptual, not a conceptual, but a different domain of relationships. And so that the mapping onto the field domain, the time and space, as we're more used to it, is not trivial, but is definitely available and is a process.
Thank you, Drew.
Okay. Well, now if it's okay, so let me go to Jeremy Rys, and then let me go to Will after that. And I'm not sure how we're doing on time.
Paul's got a quick question too in chat. I can introduce that.
My question's real quick. It's a two-part question.
Sure.
I thought we had mentioned something when you were talking to me before about Phoenix theory, about the loops and arrows being actions or entanglement forward or backward in time. And I wanted to talk more about what Phoenix said about quantum entanglement, the quantum eraser experiment, and what's it called, retro causality, things of that nature. And then my other question was about dark photons and whether or not we could make dark photon torpedoes, and whether those would be better than regular photon torpedoes.
Birthday cake.
I love the technology here. That's awesome. Okay, so let me do this. Let me talk about dark photon torpedoes.
They would really be invisible. A dark photon torpedo would be invisible, right? So it's stealth. It's a stealth photon torpedo. And that right there, Jeremy, that's why you want it. It's stealthy, right? Because the regular ones, you can see this coming from like light years away.
That's right. That was brilliant. Thank you, Jeremy. So the idea about the dark photons is that, look, we're basically expressing that that these different matter types, in particular, these different graphs that you can construct, some of them are so weirdly asymmetric that they don't break down. And we already know that in Phoenix, they have a counterpart, an antiparticle counterpart. And so when that particular asymmetric graph comes into contact with its antiparticle, of course, it forms a photon. But what that means is that that photon itself is not visible to these other smaller types of particles like electrons or protons or neutrons or whatever. And so, so we know they're dark, right? They don't generally interact with things that are smaller than them or with other types of photons, et cetera. What they do all have in common, the beautiful thing about Phoenix is that everything has gravity. So no matter what type of construction you want to have, it will always yield a gravitational presence. So with respect to your dark photon bomb, the way that you make that bomb really work so that everybody knows that it exploded is that what it would send out is a gravitational presence. You wouldn't see it, but it would rip you apart gravitationally. But the idea there is that it would hold so much gravitational energy even though you didn't know it was coming, right? And then once it lets loose, it's a ripple of gravity that really distorts all of the other gravitational things with all of the other graphs into, you know, other nonsensical shapes, you might say. So it's a very interestingly brilliant idea. I have to give you credit for that one, Jeremy. Now, with respect to the other questions that you had about time and about going backwards in time or time asymmetry, did I get that correctly, Jeremy?
Yes, and entanglement and how that
loops
and arrows and that.
Right. So generally speaking, when we're talking about vertices being connected to other vertices, that's our definition of quantum mechanical entanglement. And we can reveal that at some other point. But what we're saying is that systems of particles like 2 photons or an electron or 2 electrons can actually be fundamentally entangled. So what we demonstrate is that this entanglement is actually a property of time. Now, we don't talk about it, we haven't talked about that yet, but what we'll show later on is that there are 2 types of time that are associated with this entanglement. One is a forward motion in time, and one is a backward motion in time. But what we're saying is that that notion of entanglement being a time-oriented notion also allows us inevitably to make systems go backward in time. So for example, when we talk about a space-time diagram, we've got 4 zones, right? In one zone, you've got matter that's moving in one direction in space and in one direction in time, let's say forward in time. But in another zone, you'll have that same matter moving backwards in time. So we can demonstrate all 4 of these special relativity zones where space and time are distinct from each other by virtue of how they're entangled to each other. And what that allows us to do is to demonstrate how particles can actually move through these different domains of space and time that normally have been separated in a space-time diagram. In other words, in order for you to get from this light cone over here to a backwards flowing light cone, you got to go faster than the speed of light. And what we can demonstrate in Phoenix is that's actually not true. There are many particles that live in those other arenas that we interact with all the time. In fact, we create them in the laboratory all the time. So no pun intended on the time. But the idea is that that Phoenix demonstrates that these various points of normally of a space-time diagram are not actually separated in the way that we normally would like to think that that we're being told that they are. That there's matter types that we're already producing in the laboratory that really live in those other genres of space-time or in those other quadrants of a space-time diagram. So in other words, there's a lot more that we can do just with the matter that we're dealing with right in front of us, or the matter that we create in our laboratories, like traveling backwards in time. So did I kind of hit an answer to your question there, Jeremy?
Well, retro causality.
Retro causality, right? So the retro causality is actually a slightly separate thing. So what we demonstrate is that, remember we were talking about in the last presentation, commutators and commutator algebras and all of that stuff. Built into that is a way of talking about how particles either can be seen as I'm the particle and I'm moving, or can be seen as everybody else observing you as the particle moving. It's what we call the swarm, like a swarm of bees that you see from a distance, or how the swarm itself sees itself. Like you're one of the 50 million people in the swarm. The idea is that there are 2 different ways of doing time in Phoenix. In one of those ways of doing time, we see that things seem to be moving forward or backward according to your perspective alone. In another way of doing time, we see it from everybody else's perspective. And the reason why I say this is because retro causality is the idea of where that swarm is not looking at time in the same way as you would see time. You're moving through time in one way. The swarm is seeing all of the versions of time. So for it, time isn't just moving in one direction, okay? So the idea is that retro causality is a technique that we actually use in Phoenix in order to demonstrate why information does come from the future and go back into the past. So the present thing that you're saying, okay, I'm in the present time here, that's not actually, you can describe it that way, but there's a whole other way of describing it where the future and the past are actually influencing you in the now, okay? Where we actually take into account a future thing that's actually penetrating back into the present. And that's the retro causality that you're talking about. But we haven't given you that complete description yet here.
Yeah. So if it's okay, let me jump in and take it to Will. Where's Will at? Oops. And if he is, there we go. Will?
I will.
And where'd he go? Oh, there we go. Oh, Will, you're super faint. And there's an echo. No, I can see you, but yeah, it looks like, I think maybe, is your mic muted, maybe? Okay, and I can ask your question for you if you're having trouble with. Oh, okay. So let me mute him back out then again.
Okay.
Okay, I'm sorry about that. Yeah, Will's actually in Japan, so his time zone is way off from ours. Also, I always try and keep that in mind. It's sometime early morning tomorrow his time. So
wow.
Yeah, so it's like the middle of his night. So yeah, Will was just asking again, and a couple others had asked also about, again, just drilling down on the practical applications. Like,
yes,
what can we use Phoenix theory to build? How can we use this to modify gravity, create propulsion, things like that? And I know that's difficult because you're dealing with really big ideas, right? And so it's difficult to bring that back down. I think Todd Desiato, he put this in chat. He said engineers like something they can put a wrench around, right? So I think that's part of it. Is part of the audience is saying, how can we put a wrench on this?
Okay.
I thought it was interesting. I just want to cut in real quick.
Yeah.
That he said the second you square the matrix and take the trace, and that gives you the spin. And then if you cube the matrix and take the trace, that's when you get the mass.
You got it.
So I thought that was super interesting because we have all these experiments like Alzaphon and stuff that are telling us that spin is definitely something to do with how to get the gravity effect. And if the gravity is the third order of that, then obviously doing something in the second order is going to influence what that third order trace comes out to. So I don't know if that has anything to do with it, or am I wrong here?
No, you're not wrong at all. The idea is that that each of these different powers of the matrix, they're all connected to the exact same matrix, but the idea is that how one sees the interaction of spin able to lessen the effect of the mass, et cetera, et cetera, et cetera. They're completely combined. The best way I'm almost a little, because we haven't gotten to quantum gravity yet, and that's where all of these things get linked, okay? So in the one case, we're looking at the charges almost existing on their own, meaning the charge and the mass and the spin, they're like, okay, these are just properties of a particle. But when it comes to gravity, gravity has this unbelievable thing where it couples these things together, right? So in one case, you might have the spin being coupled to the mass being coupled to a Higgs interaction, that all of these things are actually coupled in a very a strange way. But if you know what all of those couplings are, then you have your way of determining what the heck is gravity doing. So the idea is, yes, when you are not just looking at the third order thing, or not just looking at the second order thing, there's a technique in Phoenix for being able to weed each one of these elements out and determine which of the elements you really want to preserve by virtue of a matter type. So you might be using a photon, you might be using an electron, you might be using a proton, etc. That each one of these things can be combined in a very how can I say this, in a very particular way, in order to get gravity to do what you're trying to get gravity to do. Yeah. I know it's reaching far ahead into quantum gravity in order to give you this perspective where we actually haven't given you quantum gravity yet, but that's how they're interrelated. Thank you. That was a great question, Jeremy. So hold on. Hold on.
Yeah, and that goes to the practical aspects too. And so you were talking about, and I know quantum gravity is something that you're hoping to present in the future, right? So
yes,
that's
absolutely.
Yeah, I know that we're either jumping the gun or jumping the shark. It could go either way at this point. But
I can speak to the turn the wrench thing as well. You know, we want that really bad too, because we are looking to sort of continue to develop this project and get support. And as everyone knows here, and these things, getting those experiments, getting things lined up takes resources and support. And right now we're in this, we're in a couple different phases, but one of them is what I'm leading on the software side, which allows us to do this analysis. I shared one that's the first forthcoming version of the fruits of that will be able to reproduce the muon electron production ratio that the LHCb is. We'll be able to reproduce that ratio analytically from the framework, right. and like as I suggested, it's not the 1-to-1 ratio that standard model puts out. So that's one way. It's not wrenches on pipes, I'll give you that, but it's a start on things getting measured, and we consider that a big deal. Another forthcoming one that we're working on now is also the coming up with an approximate ratio of of essentially particles that would be candidates for dark matter particles, i.e. particles that don't interact with the tiny end of the particle spectrum, we'll say, that we're in. And coming up with something that hopefully should reproduce the 1-to-5 ratio that we see, the visible to the dark. And in other ways that we'd love support and able to define, apply this analytical framework other places. So if you're interested so far, again, this is the kind of thing you can reach out to us and be part of that as well, as far as how we're researching and exploring. And then there's later steps, but that comes when some of the research is more filled in, which is what we're doing now.
Well, now if I could ask, I don't want to put, this is more from a conference perspective, right? But so I believe that I have a link to Ken's videos, his YouTube channel up. Do you guys have a website or anything like that so that I could, so basically a way to get people in touch with you without putting your emails in the open, which would be really bad. So.
So we're going to have the website hopefully up at the end of fall,
or Facebook or LinkedIn or anything like that.
Yeah, Ken, you drop your email in the chat there.
Yeah, absolutely.
Yeah, and that would work. I never put those up on the open web, right? So
I appreciate that. Thank you.
Yeah.
But please, if you've been hearing this presentation and it's calling to you and you're interested in learning more to deal in, then by all means, I would love to hear from you.
Yeah. Well, and we've got about 5 minutes left. Let me go to Harold Tavares, and then I think after that we'll probably go back to Mark Sokol. Okay. But let me go to Harold really quick. Harold, sir.
Thank you. I have one comment and one question.
Yes.
And the comment is that what you're doing is worthwhile, and I believe you should apply for a grant to the National Science Foundation. They give $256,000 at the first shot. Now, my question is this, speculative,
Yes.
Jeremy Rys asked an interesting question, at least from the sci-fi viewpoint, it's interesting. Now, looking at from an engineer viewpoint,
yes,
can an engineer look using your theory, let's say, your Phoenix theory, and decide, okay, you want to design a photon that has, like the old grenade, you put the pin or you press the fuse and it makes two chemicals and boom, explosion. Can your theory, for example, be used to at least theoretically predict, let's say, that if you use this, or several of those particles and you combine them, let's say in a torpedo, and it would create, for example, an antimatter, instantly that will annihilate, say, an enemy ship, or that create a gravity wave, artificial gravity or anti-gravity wave or whatever, or a mini black hole, something like that, a speculative can be done with your theory, in which at least, it will make some prediction by combining this particle and that particle in certain way, something that can be engineered into something, either a sci-fi or preferably as the real thing. What are your thoughts?
Oh yeah, no, it's funny because I've been, for the last 9 years, we've been looking for practical applications, like what can we actually do with this? And one of, so what you're talking about, for example, I want to bring it back a little bit from the blowing up technologies, but at least, for example, with respect to nuclear energy, right? So we've got a lot of various spin-offs that describe, well, what the heck are we talking about when we talk about nucleons? And how can we describe the periodic table of nuclear matter? And then how do we use that in order to create batteries, for example, to store the most amount of energy in a nucleus that's possible, and then how do you release it, right? So there are a lot of things that we've investigated and that we can bring together in order to explore modern technologies. And so the answer is yes, there's a lot of yes going on with that. In other words, we know how to create antimatter. We know how to create antimatter in a way that it actually amplifies the production rate of the antimatter. We know how to use nucleons in order to store the maximum amount of energy, and then how to release that energy. We know how to utilize this new energy carrying technique in order to create, I guess if you want to create an explosion with it, you certainly could, but how to not do that, but in a controlled way, right? So advanced systems of nuclear energy, you might say. But what's been very important to us is how do you create negative energy? And then how do you store that negative energy in order to manipulate, create an Alcubierre warp drive? So that's been a really big zone for us as well, that we've figured out ways to do. So there are some very standard ways of creating negative energy, and then there are some very advanced propulsion ways of creating negative energy. So you have various forms of warp engines that come out of this theory. And then comparing the types of technologies that we can produce with standard ways with what we observe from UFOs, for example. Why is it that that a standard observation of the UFO at night has all of this dancing plasma-like light shows going on around it? Why is there generally a static electric field in the vicinity of seemingly these advanced propulsion systems? Why is there no sound, for example? Another interesting question is, why, historically do we might think that gold might be some interesting, atom that a various UFO might actually give a hoot about, what the heck's going on with things like gold versus any other sort of nucleon of the periodic table. So there's a lot of questions that we can actually answer and address fairly directly when you actually exploit what Phoenix is saying about these fundamental particle types. But it's a great question.
Wonderful.
One more question.
Well, actually, Harold, we're just about out of time. So
Okay.
if that's okay, yeah, let me.
That's
So
okay.
Mark is getting ready to go again. So let me do this. Let me mute everybody out, and I want to put this back on gallery view. Okay, and I should apologize because we did have lots and lots of questions coming. But everyone, please put your hands together again for Mr. Ken Griggs and Mr. Drew O'Meara. Gentlemen, thank you both very, very much. And I should apologize. We're just pushing up against our time constraints here.